I know it's been a long, hard break without any new physics videos to watch, but never fear, the wait is over. This semester we are going to start looking at waves, and today we'll look at just some general properties about how we describe waves in terms of how big they are and how they move and things like that. There are a number of animations in this presentation, most of which were done by this guy, Mr. Dr. Dan Russell, so thank you for your contributions to our lives. Okay, if we look at kind of a snapshot of a wave, by snapshot I mean waves are generally moving either in space or time, but this is frozen in both. Then we can describe different aspects of that wave. We have the amplitude, which is half of the entire height from crest to trough. Crest is the peak, trough is the bottom. So be careful not to think that the amplitude is the entire height. It's half of that. It's often defined as the distance of maximum displacement from equilibrium, where equilibrium would be the line going through the middle here. Wavelength, we use this fancy symbol lambda, and it's the distance from one point on the wave to an identical point in the wave cycle. Here, be careful not to say, well, here and here are the same heights, so that's a wavelength. No, it's got to be the same height and the wave is having the same slope, so to speak. So it doesn't matter where on the wave, it could be here to here. As long as it's one complete cycle, that distance will be the same everywhere for a wave, and that's what we call the wavelength. Frequency and period, we'll talk more about these when we look at the quantitative calculations with waves, but frequency is how many waves are coming by per second. The period is the time for one wave. So they're interrelated, but one is time per wave and the other is waves per time. Also, we have this term here, the medium. That is the, as you can read, what the wave is traveling through. So if we have a wave on a string, then the medium is the string. If we have a water wave, then the wave is water. Sound waves require air to travel through. You don't have any sound in space. So the medium of sound, we would say, is air. By the way, the plural of medium is media. And so this has other meanings. The media, when we talk about news sources and whatnot, they are what the information is traveling through. It is plural, by the way, so you should say the media are biased or something like that rather than the media is. Also, you might think of a medium as somebody who can contact the dead or something, but again, it's similar meaning where it's the go-between, right? The thing that's carrying the information. In this case, for physical waves, it's carrying energy, which can be information, can be coded into information. All right, we have a couple of different types of waves that I want you to be familiar with, defined by how the waves are moving. So you got this wave here, and we say that the motion of the wave, in this case, would be to the right, but the medium itself, the substance, is oscillating up and down. So wave goes this way, medium goes that way. That's perpendicular to each other. And anytime we have that, we call that a transverse wave. And you can remember that because the T is perpendicular. So wave motion, particle motion are perpendicular. Another point here is if you look at the medium doesn't get transported anywhere. You have a displacement, a net displacement of 0, right? It's just oscillating back and forth. So waves do not transport the medium from one location to another. It just transports the energy from one location to another. All right, so this is one type. Another type is what we call a longitudinal wave. In this case, the medium and the wave are both going in the same direction. So we say that the motion of the wave is parallel to the motion of the medium. Again, it might look like an optical illusion. It seems like these particles are traveling, but that's why these ones are highlighted in red, just to help you pick out a single dot. And you'll notice that each dot is just going back and forth. And if you're careful and keep your eye on any of the black dots, it's true for all of the dots. They're just going back and forth. So again, what's being transported is the energy, not the medium itself. Okay. Now, with that second type of wave, the longitudinal wave, these are often called compression waves. we still have wavelength and amplitude. It's just not quite as easy to see. So here's the transverse wave. Obviously the wavelength is easy to see. The amplitude is half the height of the wave. In this case, the wavelength is the distance from compression to compression, or from expansion to expansion. That's the term your book uses. I like the fancier term rarefaction. To rarefy is to spread out, the opposite of compress. To find the amplitude, that's a little trickier to visualize. Essentially, it's how bunched up the compressions are compared to the expansions. With air, when we think about sound waves, these are longitudinal waves. And so it's essentially the difference in the pressure between the high pressure locations and the low pressure locations corresponds to amplitude. So you still have all the same wave properties between the two types. All right, one other little distinction between types of waves, this isn't too important, but I thought I'd point it out real quickly, is you can have a single pulse, in which case wavelength doesn't really apply. Or you can have, if you imagine somebody hanging on to the end of a rope and jiggling it up and down, and you have a continuous disturbance, then you can get what we call a continuous or periodic wave. And you can have the same thing for both transverse and longitudinal waves. All right, now let's look at a couple of other types of waves. If you've ever been to a football game at Mackey Stadium or something like that, and you've done the wave, we can call that a people wave. And it's got a lot of properties of an actual wave, but some properties aren't identical. For one thing, the wave moves, but the people don't, right? When you do the wave, you don't end up in somebody else's seat. And if we were going to call this more like a transverse or a longitudinal, we would say this is a transverse wave because the people move up and down, but the wave moves side to side. It's not really a true wave because there's not energy being transported. Maybe if they were holding hands and one person actually lifted the arm of the next person, that would be more like a real wave. But anyway, a couple of other waves, water waves, are not perfectly transverse or longitudinal. If you look at a single particle, it would actually be traveling in kind of circular motion. Again, there's no net transport in the ideal situation. If there's not any friction going on, rubbing with the bottom of the ocean or whatever the water is in. But the particles do travel in circles, and the further you go down, the smaller the radius of the circle that it travels in. Now, you might think about waves crashing on the beach, and those don't seem much like this picture here, this nice, gentle, circular motion. Well, what's going on there, if you have shallow water, you're interacting with the bottom, and that's disturbing the wave. For one thing, there's more friction down here, so the top of the wave is going to move relative to the bottom of the wave. It doesn't... You know, a water particle here doesn't travel all the way to the shore, though. It just kind of sloshes and gradually moves. So that's one thing that happens. Another thing, the waves will start to swell up because the contact with the motion of the water down here hitting kind of pushes everything up, and that's why waves get bigger near the shore. If you were in the middle of the ocean, a tsunami wave could go under you and it could just be a little bump, but that wave might be really deep in the water, and so by the time that starts hitting the shore, that starts pushing it up really high. The other thing that happens is that contact with the bottom starts slowing the water lower down, and the water at the top of the wave doesn't slow as much, so that's what causes it to tip over, and when you get crashing waves, good for surfing and all of those things. All right. One other type of wave we're going to look at, and we're not going to do any calculations with complicated waves like water waves and this Rayleigh wave, but just so you know, there's other types of waves out there. So Rayleigh waves are kind of like, they are a type of earthquake waves. You get several waves produced in earthquakes, what we call S waves, P waves. There's another type called love waves, and these ones called Rayleigh waves. And what they are is similar to a water wave where you have both motion vertically and horizontally. In this case, it's a bit more elliptical, and you'll notice this guy here is going counterclockwise, but down here, if you watch closely, this guy is gradually going clockwise. So you get kind of more bending going on. These are actually the most destructive earthquake waves. They are responsible for most of the surface shaking. And it's not just earthquake waves. If you hit your desk, there I hit mine, a wave propagates through your desk, and that wave through a solid material is a Rayleigh wave. All right, that's all there is. There's another video for example problems and calculations. Thanks. Bye.